Okay, so today we will start talking about tensor products of R modules. Okay, now until now we talked about the notion of tensor products for two modules M and N, which are both Z modules. So given two abelian groups, we define their tensor product. Okay. Now what we want to do is to sort of do the same thing for modules over other rings. Okay. Now to do this, I need to recall briefly the notion of a right module as well, because that will enter the definition. So what is a right R module? Okay, we know what a left R module is. To recall, a right R module can be thought of as the following. M is a right R module if it has an abelian group structure. So an abelian group, so let's say it this way: a right R module is an abelian group M together with a right multiplication, together with a map M cross R to M, which we will write like this: M comma R mapping to M maybe with a circle on the dot. So goes to M dot R. Okay, so this you think of as multiplying on the right, satisfying the following axioms, okay, such that the following axioms are true. M acted upon by 1 on the right gives you M. M acted upon by R1, R2 gives you M R1 followed by followed by R2. And thirdly, if I take M1 plus M2, then that's just the M2R. Okay, and this is for all M1, M2 in M, R in R. Okay, so the key point here is that this axiom, the second axiom, is what differentiates a right module from a left module. If you did the same thing on the left, then R1, R2 on M would be you first act R2 and then R1. Okay, so here you are acting R1 then R2. And so recall that there is also so there is this thing called the opposite ring. So recall this from Algebra-I. The opposite ring is nothing but the ring R, but with a new multiplication, with a multiplication which is redefined as follows. Okay, so you say, okay, A multiplying B is now B times A. Okay, where BA now just means the multiplication in the original ring R. Okay, so you just reverse the order and multiply. Okay, that's a new multiplication, and the ring R with this new multiplication is usually denoted R op. So the addition is the same, the multiplication is the opposite order. And recall the following fact that modules, right R modules are the same. So right modules over the ring R are the same notion as left modules over the opposite ring. Okay, so when I write R modules, I always mean left R modules. Okay, so this is always left. If I don't specify whether it's left or right, then it's left. That's our convention. Okay, so this is a brief introduction or recall of what the right R module structure was. Now let's define tensor products for R modules. Now it turns out that to define the tensor product for R modules, what you need actually is a right R module M and a left R module N. Okay, given this pair, what we can define is their tensor product, okay, which we will denote the tensor product M tensor N over the ring R. Okay, now just to give you some heuristic motivation for why one would need this sort of combination, a right module and a left module, okay, in this order. The first component M must be a right module, the second one must be a left module. So recall, so here is a little bit of heuristics for why we need this. So recall that when we talked about tensor products for Z modules, so what we did was, so suppose, imagine for the moment M and N are only Z modules and we defined that tensor product. The thing we did was, so there was a bilinear map from M cross N to the tensor product, which we denoted M comma N going to, so that map was called alpha, and we also had a alternate notation. We called this element as M tensor N. Now this map was Z bilinear. Okay, and recall Z bilinear means that if I replace M by M1 plus M2, it distributes. Similarly, if I replace N by N1 plus N2, it splits into two pieces. Or another way of saying what bilinearity is if I multiply N by some integer A, okay, then this scalar A can be pulled out. So recall that we had this okay. So multiplication by an integer, whether you multiply the first component or the second component, it is the same answer, okay, and that's the same as this element M tensor N multiplied by this integer A. So this was what bilinearity implied, okay. But now imagine that you were trying to do this for, you would want, when we construct the tensor product over an arbitrary ring, we would still want this property to hold, okay. So here, so suppose for the moment we replaced R, Z by R, for example, okay. So imagine now I take this scalar A coming from the ring R, okay. So here's what I would want my tensor product to satisfy. I would want some kind of a bilinear map from M cross N to M tensor N. Now what I'm going to call M tensor N eventually. So this bilinear map, I would like it to satisfy. So bilinearity means if I multiply N by A, then I should be able to sort of move that scalar out and move it to the first component, okay, like what was true in the case of the integers. So if this is what I want to happen, multiplying N by A is the same as multiplying M by A. Now the point is, suppose I want this to be true, but imagine what would happen if you multiplied N by a product of two scalars, okay. Then this wish list, the thing that we want to be true, will imply the following. First, I can push the A out, okay, because AB of N is just A acting on Bn. So this will just give me AM tensor Bn, and again I can do the same thing. I will get BAM tensor N, okay. So that's one way of doing it. On the other hand, I can just think of AB as a single scalar, right. So M ABN, and now by this what I want to be true, that scalar AB can be moved to the first component. So this is what I would get, okay. And now observe that if I tried, if I want this to be true for an arbitrary ring R, the point is arbitrary rings are not necessarily commutative, okay. And so if my map here, if I want this tensor product map to be bilinear in this sense, okay, that if I want to be able to move the scalar A from the second component to the first component, then I'm already in trouble, okay. So I notice that then this and this must be the same answer, okay. But of course that's not going to be true in general. No reason to expect it to be true, because AB and BA are not necessarily the same thing in a non-commutative ring. Okay, so this is sort of the trouble here. Okay, and this is sort of why you can't really take the tensor product of two left modules. Doesn't make sense. This is remedied. This problem is remedied by making the first component a right module and the second component a left module, and in that case this problem doesn't arise. So what we will do is say that okay, we would like our tensor product to have the following property, that I can push this scalar m a across and multiply it by m, but m is only a right module. So this is what I would want to be true. Okay, so I multiply m by a, the scalar multiplication, on the right. Okay, and then you will see that this problem goes away. Okay, so let's go ahead and make the formal definition. This is just a heuristic motivation for why one module needed to be right and the other needed to be left. Okay, so here's the formal definition of a tensor product. Let m be a right module and n be a left module. Okay, a tensor product of m and n is a pair, again like in the case of Z modules. So what is it? It's a pair p comma alpha, maybe we'll call it t comma alpha, okay, which satisfies a certain universal property. Okay, satisfying the following properties. One, so what is T? T is a Z module. Okay, so if you take the tensor product of two R modules, the answer is only a Z module. It's only an abelian group. What is alpha? Well, alpha is a map from m cross n to T, which has the following property. Okay, m comma n maps to whatever it is, alpha of m comma n, alpha satisfies bilinearity in the following sense, that if I replace m by m1 plus m2, then I get a sum. If I replace n similarly, okay, and the third property is what we just talked about heuristically, which is that if I scalar multiply n by a scalar a, then that answer should be the same as right multiplying m by a and leaving n as it is. So this is now true for all scalars a from the ring R and for all m and n, for all m in m, n in n. Okay, so this third property is the new notion. The other two are similar as before. So these here again, this is for all m1, m2 in m, as expected, n1, n2 in n. Maybe also I should say for all m1, m2 in m and n, n1, n2 in n. Okay. Now, so this alpha satisfies these three conditions. This third condition, or maybe the set of these three conditions, is called. So we say that alpha is an R balanced map. Okay, meaning it's bilinear in the sense m1 plus m2 and n1 plus n2 will give you the expected answer, but this new property here, that this a can sort of be moved across from the second component to the first component, that's sort of this notion of being balanced. Okay, so in this terminology, what we are saying is that a tensor product of m and n is a pair t comma alpha. T is a Z module, alpha is an R balanced map from m cross n to T. Okay, such that satisfying a certain universal property. Okay, so this R balanced is what replaces just bilinearity. When R was Z, we only required alpha to be bilinear, when you take an arbitrary R module, arbitrary ring R, then we also require alpha to satisfy this third property. Okay, such that it has the following, universal property. What's the universal property? It says that given any such pair, P comma F, okay, with satisfying the same three properties, P a Z module, F an R balanced map, okay, and F an R balanced map, then there exists, so let's draw the diagram now, then there exists a unique map. So how does the diagram go? From M cross N to T, that's my tensor product. Now what I'm saying is, given any P and any F, any R balanced map, I can find a unique map from T to P. Okay, there exists a unique, and what kind of map? Now T and P are both Z modules, or they are abelian groups. So there exists a unique Z linear homomorphism, or a homomorphism of Z modules, Z linear map F tilde from T to P, such that this diagram commutes. Okay, F tilde composition alpha gives me F. Okay, so you can see it's quite parallel to the earlier story of tensor product of Z modules. The only new ingredient is this new notion of being a balanced map. Okay, so many things are now that you have seen how to construct tensor products for Z modules, it's very easy to see how to do things here. So let's make various remarks. So observe, firstly, remark, as before, you can think of all this as in terms of categories and functors, that this is a certain initial object in a suitably defined category and so on. But the key point here is that by similar arguments to what we did before, if I have another tensor product, if T prime alpha prime is another tensor product, then that map which you get, then the following is true, that there is a unique isomorphism between them. Then look at this, M cross N, T prime, T alpha alpha prime. So by the universal property, there is a map alpha prime tilde in this direction. Similarly, T prime is a universal object, meaning it's also a tensor product, right? It has the same universal property. So you can also show that there is a map alpha tilde in the other direction, right? So these were the same arguments which we gave for the case of Z modules, and one can show that their compositions are identities. Okay, then alpha tilde composition alpha prime tilde is just the same as alpha prime alpha is the identity on T, and okay, by the same arguments as before, by previous arguments. Okay, so what it means is that tensor products, if they exist, are unique up to a unique isomorphism. Now let's just show existence, and the proof of existence is more or less the same as we did in the case of Z modules, which is we proceed in two steps. We first look at the free module, and then we look at the quotient module, right? These two same very similar construction. So existence, let's do the same thing. Let's take the set S to be M cross N. Think of it only as a set, no additional structure. Let's take F to be the free module. So maybe F comma gamma, if you wish, is the free Z module on S. Okay, so recall what that means. Well, that just means the elements of F look like they're sort of linear combinations, if you wish. C, Mn, E, Mn. Okay, now E, Mn are mn's come from the set S, meaning from the cross product. Okay, and I am only taking the free Z module, so this is still elements of Z. Okay, so any element of F can be written uniquely in this manner, and we also have this map. So from M cross N, this map gamma to F. What does gamma do? Gamma just takes the ordered pair M comma N and sends it to that particular indicator function, as we called it, E sub Mn. Okay, and now the next step is to go modulo a certain subgroup. So F is an abelian group, I have to go modulo a subgroup. So if you recall how this subgroup was constructed in the case of the tensor product of Z modules, let's just do a similar thing. What is H tilde? H tilde is the subgroup of F generated by the set of, by the following elements of the following form, generated by the following subset, if you wish. Take all elements of the form E m1 plus m2 comma n minus E m1n minus E m2n comma, what other elements should I take? So okay, so this is for all n union, a similar thing with n, and finally, so recall these were the two things you needed to satisfy the first two properties, but now we have this R balanced condition, so we also throw that in. Okay, so this is for all m in M, n in N, and now A comes from the ring R. Okay, so this is the key thing, that now the elements of the ring R are now involved in this. Okay, so this is a new, this H tilde is different from the previous H, in the sense that only involved the first two subsets. This also has this third additional set of elements. Okay, so as before, it's a subgroup. F is abelian, so this is a normal subgroup. So I can look at the quotient, okay, which is what we did here. So this is the quotient group, and that's going to be our, so this is the quotient map which sends F to its quotient. So this quotient finally is going to be our tensor product module T. Okay, so we define T as the quotient, and we define this map alpha from M cross N to T to just be the composition. So define alpha to be the composition, pi composition gamma. Okay, so now the claim as before is that this satisfies all the properties that we needed to satisfy. So observe as before that okay, T is a Z module is obvious by construction. Okay, claim is alpha satisfies the R balanced condition. Okay, alpha is a map from M cross N to T. Why does alpha satisfy the R balanced condition? So I'll just check the new axiom. The earlier ones are similar. So what is alpha acting on M comma An? Well, by definition, this is just pi composition gamma of M comma An. And if you see what that is, this is E of M comma An, and pi just means you take its coset modulo H tilde. Okay, so maybe I'll just write it like that, plus H tilde. On the other hand, if you compute Ma comma N, by the same token, this is just E of Ma comma N plus H tilde. Okay, but observe these two cosets are equal. Why? Because the difference between these two elements, Man minus Ma comma N, this difference is in H tilde, so these two cosets are exactly equal. Okay, and the same sort of argument works for the other two axioms. So alpha is indeed R balanced. Okay, now by the previous sort of argument, we'll again show that this has the required universal property. Okay, so let's check that T comma alpha has the universal property. Okay, so what does that mean? We have to take any pair M cross N to P and then construct a unique map from T to P. Okay. Now we proceed like we did in the previous case. Okay, for Z modules. What did we do? We said, okay, first we know that the free group F, the free Z module, that has a universal property. Okay, which is that given any set map from M cross N to a group P to a Z module, it gives you a unique map from F to P. Okay, so this is a map. Let's call it G. Okay, so there exists a map G from F to P. Okay, this is a Z linear map satisfying G composition gamma is F. Okay, and this is by the universal property of free abelian groups or free Z modules. Now, second universal property that we need is we go to the quotient F mod H tilde, and we said that the universal property of the quotient was the following, that if this map G has a property that its kernel contains H tilde, then there is a unique map from the quotient to P. Okay, so by the universal property of the quotient, okay, to do this, well, we need to first check, before we use the universal property, I need to first check that the kernel of G contains H tilde. Okay, in other words, I should check that every element of H tilde, the generators, it's enough to check the generators. I need to check that the generators of H tilde all belong to the kernel. Okay, so let's pick various generators. So I will just check it on the third kind of generator, the new one that we are dealing with. The other two verifications are like before. So let's take the generators. What's one of them? M comma an minus E M a comma n. Okay, so what am I doing here? I am trying to write out the generators of H tilde. Okay, and this is one kind of generator. Okay, now I need to check that this belongs to the kernel of G. Is this true or not? Okay, let's check. Let's apply G to this. Okay, now G is a group homomorphism. Okay, it's a Z linear map, which implies that this is just going to be this. Okay, but then what is this? Well, this is just G composition gamma of M comma an minus G composition gamma of Ma comma n. Now, what was the property of G? Well, G gamma was F. Okay, so this is F of Man minus F of Ma comma n. Okay, but observe that is 0 because F was given to be R balanced. Right, we are only trying to show the universal property relative to pairs P comma F where F is R balanced. So what this means is because F is R balanced, that element, this particular generator of H tilde in fact belongs to the kernel. Okay, so what we have shown is yes, it does. Okay, now because it does belong, now the universal, I mean, you have to check the other two generators similarly, the other two kind of generators. So this by the universal property of F tilde, we conclude that there exists a map G tilde from F mod H tilde to P such that, you know, it's again a Z linear map. Okay, there exists and G tilde is Z linear. So all this is more or less a repetition of the arguments we gave earlier. So now finally, what does this mean? This means that we have shown the universal property because I have two commuting triangles. So on the one hand there is G, the other hand there is, so this was F mod H tilde. So there is this map G tilde. So what do we have? We have two commuting triangles. So G composition gamma was F, G tilde pi was G. Like we did earlier, you substitute G and conclude that this is F. Okay, and of course this means pi gamma was exactly our alpha, so therefore G tilde alpha is F. Okay, and that's exactly what we need to prove. So G tilde alpha, this map here is alpha. So we need to show that you can find a map So I mean, like we did earlier. So let's call G tilde as F tilde now. So let's just define F tilde as just the map G tilde. So we have shown that this outer triangle also commutes, because the two smaller inner triangles commute, the outer triangle commutes. Okay, therefore done. So we have shown that the pair PF, the pair T comma alpha, so this is T, satisfies the universal property. Okay, and again, I mean, not quite, we haven't fully done it, because we have to show such a G tilde as unique, but that again is the exact same proof as before. So I'm just going to leave that part as an exercise. Prove that there exists a unique such map F tilde. Okay, there's a unique Z linear map F tilde such that F tilde composition alpha is F. Okay, and again the argument is similar to what we did before, that the image of alpha, so again you have to use the same facts as before, that the image of alpha generates the subgroup, I mean generates the group T as a Z module. Okay, so very good. So we have shown the existence of the tensor product, and again remark on notation, just like we had in the case of Z modules. If I have M cross N to T, this map alpha, so alpha, remember, was E M N bar. So we give this a name, we now call this again little m tensor little n. Okay, just more or less the same notation as before, but we understand from context what tensor product we are talking about. So if we are thinking as we are looking at the tensor product of M and N thought of as right and left R modules, then this M tensor N just refers to this particular element which I constructed just now for you by going modulo H tilde. Okay, so observe that there is also the need to be careful here is because of the following. If M and N are R modules, I can ignore the R module structure, think of them only as Z modules if you wish, right, just the abelian groups. So I can also construct another object called M tensor N Z. Okay, this is a different object. This is, if you wish, this has a different universal property, which is with respect to the maps, where I just take F to be the usual bilinear map without being balanced. Okay, for such maps, you get this universal property. So that object is M tensor N over Z. Okay, that was our previous construction. Whereas if you look for M tensor N over R, that's a different object that has a universal property with respect to the R balanced maps, and its construction is different. Okay, and in fact, you can sort of see how these two constructions mesh together. The earlier construction, when we talked about M tensor N Z versus M tensor N R. Okay, if you notice, the construction proceeded along the same lines. I first took the same free abelian group F, but the difference lay in what I went modulo. Okay, in this case, I go modulo H, which was only the subgroup generated by the first two kinds of generators. Whereas here I go modulo H tilde, which also has a third kind of generator. Okay, so observe, H tilde is actually bigger than H. Okay, H is a subset of H tilde. So if you wish, as an abelian group, if you go modulo H tilde is actually larger than H. So F modulo H to F modulo H tilde, you get a map. You get a surjective map if you wish. Okay, from just general principles about groups, that G modulo a smaller subgroup versus a larger subgroup, there is always a quotient map, right? So this is called the third isomorphism theorem and so on. So this is we are not going to use any of this, but just to keep these concepts separate in one's mind, it's useful to know that you can actually think of M and N only as Z modules and try doing the same construction, but what you're doing there is constructing a different object with a different universal property. And if you want to compare these two objects, this is the relationship, that the Z module that we constructed in the first instance actually has a surjective map to the Z module that we constructed in the in the second set. Okay.